Differential thermal analysis method was introduced by Le Chatelier in 1887 and was modified by Robert Austin in 1899. Burgess in 1909, Norton in 1939, Grimm in 1951, and Folberry-Vogel in 1958. Since differential thermocouples were used, hence the technique came to be known as differential thermal analysis. Differential thermal analysis can be described or defined as a technique in which the temperature differences, referred as delta T, between the sample and a thermally inert reference material are continuously recorded as a function of furnace temperature represented by Tf or time T, sample temperature represented by Ts, and reference temperature Tr. In differential thermal analysis, heat effects associated with chemical and physical changes of a substance are recorded when it is heated at a linear rate. Thus, a differential thermogram consists of a record of the difference in sample and reference temperature. Differential temperature is reported as delta T and is plotted as a function of furnace temperature, sample temperature, or time. An ideal differential thermal analysis curve is illustrated in the figure. Generally, sharp endothermic peaks indicate changes in crystallinity or fusion processes, whereas broad endotherms signify dehydration reactions. In most of the cases, physical changes give rise to endothermic curves, while chemical reactions result in exothermic peaks. Therefore, the endo and exothermal peaks appearing on the thermogram gives us information regarding the enthalpic changes. Thermogravimetric analysis and differential thermal analysis are complementary techniques because the information obtained by one technique can be substantiated by the application of the other. Theory of differential thermal analysis. Boersma deduced the expression for the peak area by employing a sample block constructed from an infinitely high thermal conductivity material like nickel, in which the sample holder was considered to be geometrical in shape. He gave the following expression: integration from T1 to T2 delta T dt is equal to Qa square upon 4 lambda, where lambda is the thermal conductivity of the sample, A is the radius of the cavity filled with sample, delta T is the differential temperature, Q is heat of transformation per unit volume, T1 and T2 are the times at the beginning and end of the peak. If a spherical metal sample container is employed, the above equation becomes integration T1 to T2 delta T dt Qa square upon 6 lambda. And in the case of a one-dimensional flat plate, the equation, the 6 lambda modifies to 2 lambda. For a spherical holder of radius A, the equation modifies to integration T1 T2 delta T dt is equal to Qa square upon 6 multiplied by 2 upon lambda C plus 1 upon lambda S, where lambda C and lambda S are the thermal conductivities of the ceramic material and sample respectively. If delta C is infinite, the equation gets reduced to equation 2 for a spherical nickel block. These equations show that the sample used as, as a producer of heat and a heat measuring resistance in which the flow of heat develops a temperature difference that is to be measured. To separate these functions of the sample, Boersma suggested the use of sample cup and reference cup, and the temperature difference was to be measured from outside the sample and reference materials. The peak area depends upon the sample heat of transformation and calibration factor of the instrument. Lukaszewski pointed out that whenever heat transfer occurs between the heat source and calorimeter, it takes place by conductive and radiative mechanisms. Heat exchange between block calorimeters and reference or sample materials occurs by conductive mechanism only. There occurs periodic heat absorbing, that is endothermic, or heat generating, that is exothermic phenomena in the active sample of the system as a function of time, temperature and position in the medium. Such heat transfer takes place by complex mechanism where the physical properties of the sample rapidly changes.